Oh, hi there. I'm Art Turlip. You may have seen me in such shows as The Electric Chef and ECE 2002. But I have to tell you that school is no joke. In fact, you kids should stay in school, don't do drugs, and stay away from alcohol. If you do, you'll stay on target for graduation. Bullseye. Welcome back, everyone, to another fun-filled session of ECE 2002. I'll be your host today, Art Turlip. Okay. Today, we're going to talk about ordinary differential equations. And we are just going to talk about ordinary differential equations. So, if you know how to do ODEs really well, you can probably skip this one. If you want a little recap and you're not sure about some things and you want to learn a couple extra things on the side, go for it. Let's do it. So, first of all, what are we even doing here in ODE land at this point? Why are we here? Why do we care? Well, we're coming from basic circuit analysis, right? And what we're going to find is that as we add more elements and time dependency to our signals, we're going to end up with equations for our analysis that are differential equations. And we're going to show some of that next time with some very simple circuits that you may have seen before, but we're going to add those time dependencies to them. So now we have a differential equation we have to solve. Today we're going to be building a little bit of our toolbox that is learning how to solve those ODEs that we're going to run into next time so that we can just push right through. Now, that's great and all, but this is kind of going to end up being a little bit of a dead end. And to be quite honest, once we do the ODE stuff, we're kind of going to throw it off to the side because we're going to discover something even better that we're going to want to use to kind of solve problems for us. It's not to say ODEs are useless, it's just we have other tools that we're going to focus on later on in the semester. So long term, we're going to kind of discover some new tools that overcome our need for the ODE stuff. And they're going to end up providing some key insights for our frequency analysis. So where we're going is after we get through all the ODE kind of analysis, we're going to learn about convolution, impulse responses, the Laplace transform, which is awesome, super powerful tool. And the and transfer functions. So, and that's going to take us right into transformed circuit analysis, which eventually, we'll look at frequencies. Okay. Oh, little side notes here. I don't know if I cover these or not, but I'm going to anyway. IE is like an equivalency, like, hey, that is to say, I say something and then I just reiterate it. E.g. is an example. 3 dots up is therefore, 3 dots down is because. I very rarely use this one, mostly because I haven't run across it too much. I use therefore very frequently. So there you are. All right, a little history. This is Euler, this guy here. So you too can wear pants on your head and become a genius. I don't know. This looks like pants to me. I'm not sure what's going on here. Guess it was the style. But anyway, Euler is a pretty cool guy. He followed on the heels of Leibniz and Newton. So this is just kind of after the end of the 1600s, coming into the 1700s. So Euler's, heyday, I guess you could say, was after he went blind. Okay, so this dude goes blind and still is pumping out a paper a week. It's ridiculous. This guy is absolutely crazy. You should look him up sometime. Started off in religion and philosophy and then moved into math. Pretty much pure math, actually. But he also has some applied stuff. And the stuff that he comes up with ends up getting used everywhere. This is how math works. But he was well connected with the Bernoulli family. So any of you that have taken probability theory are have heard that name a million times over. Bernoulli trials probably. So a lot of probability stuff there. There's also some other functions that they developed in that family. But he's following on the coattails of Leibniz and Newton, okay? And there's sort of a feud between these two. And I'd be remiss if I didn't mention it to you guys at some point. But Leibniz also invented calculus, by the way. He just did it in a different fashion. So he actually used more of an infinitesimal system than a limit argument. And I actually like Leibniz's approach better. And I think they are two valid different approaches, but I think Leibniz makes a lot more sense because it still uses this sort of discretized argument that I think makes a lot more intuitive sense to the human mind. But that's kind of philosophical. My third son actually is named Newton, so I'm not, completely opposed to Newton. Not my third son, my third kid is Newton. But anyways, there you go. So down here we have the most important equation in the world. E to the pi I plus 1 equals 0. You've definitely seen it. This is Euler. And that little e there, that's Euler's number. Super handy. And we have multiple representations of how we can write and express this and that number itself. Okay. You know that e to the I v is just, a combination of cosine and I sine. You've probably, I hope, seen this used for some kind of sort of phasor notation or thinking about things in terms of, a waveform and its associated phase. If you haven't, we'll get there. So other stuff that he's done and contributed to: number theory, graph theory, tons of universal constants, okay? Flow equations, which, if you're doing stuff today, you think, you do it on the computer. These guys had no computers, all right? They had, their little abacuses. That's it. Infinitesimal calculus, logic, set theory, music theory, and all kinds of other stuff. So this is, if you ever want to feel small, look up some of these guys, and it'll make you feel dumb real quick. All right, so let's talk about this special function, e to the x. So we can write this as a series, as you should probably be familiar with. You should know this equation. If you don't, good thing to memorize. Why is it so special? Well, it satisfies this particular requirement. And for differential equations, this is going to be very useful for us. You should know that it does this. All right, so I got a couple little thought problems for you guys here. You don't need to do these as part of a homework and you're not going to be tested on them, obviously, but, can you find a function that does this? And I encourage you to stop the video and work through this a little bit, have some fun with it. Can you find a function that does this? I'm going to tell you this one is a lot harder. And I'll tell you that it also involves the golden ratio as kind of a hint. But I don't know, I've seen some pretty neat, I saw a neat video on this the other day. I had never really thought of it, and ran across it and thought, oh, that's a really, really cool problem to try to do. So the next question you want to ask yourself is, are these ordinary linear differential equations, or are they even differential equations? So we'll get to that because we got to define it first. But, look at these for yourself and come up with what you think the answer is. Post it to right space. I don't care. All right, so e to the x allows us to solve many, but not necessarily all, but pretty much all the ODEs that we're going to be working with are going to involve e to the x in some way, shape, or form, because we deal with waves, right? We deal with waves. Our signals come in waves. They're oscillating, they repeat over time. So it's no surprise that this is the case. So fortunately for us, the analysis the equations are actually quite easy. All right, so let's get into what an ODE is. because I promised you guys we'd do some math today. It's ordinary because we're dealing with just one independent variable, t. This is a t. That's my t. All the derivatives are taken with respect to time. So although we have a couple different functions kind of floating around in here, we generally are just dealing with an input, x of t, and our output, or what we call the forcing function, y of t. And in between these two, we're kind of shoving x into this operator box, if you will. The differential equations that we're applying are linear operators, meaning that when we put x in, y is just a linear combination of operations on x. And a linear combination is just something times x, or something directly applied to x. And it can be expressed in this fashion, where it's a distinct operator attached to it. So differential equations obviously can get a lot more complicated. Even linear ones can get more complicated than this, because you can have functions of t floating around everywhere. You've probably seen, mu t floating around as like a coefficient tacked onto stuff. So, there's a lot of different ways. This is all we're going to be concerned about in this class for right now, and then we'll develop other tools as we need them, if we need them. Fun fact here, this is a shout out for you comp sci folks. I feel like you guys kind of get the short end of the stick sometimes when you take, doing the comp sci route or whatever. Because, if we're taking EE courses, it's all electrical engineering oriented. Well, I'm from out in La La Land with math, so I'm going to go ahead and give you guys a little bit of treats here. So here's your treat, if you want to call it that. Reverse Polish notation. Okay, if you haven't heard of this before, it's kind of wild. But basically, all the math notation that we use is completely freaking backwards. When you think about it, we read from left to right. And in fact, when we write a diagram, this is the first thing that comes to mind when we talk about operators, right? You have an input, you stick it into an operator. We call this input an operand, by the way. And then you get an output on the right. We read from left to right. But in fact, when we write it, it looks like this over here. What the heck? So some smart people said, hey, why don't we use this thing? We'll call it, for whatever reason, reverse Polish notation. And it actually is more technically correct. And as it turns out, and this is interesting to you comp sci folks, it's actually a little less language to write depending on how the operator is constructed, because you don't need to directly apply a lot of the parentheses or modifiers to terminating where your operand representation stops. Because if you have it up front, well, then everything from here to here is your operand. Then it's, it's the operator, and etc. But you're not really sure where the beginning and end. So anyways, something to look into if you're interested. I could talk all day about weird tangents like that, but there's your treat. All right, so here we go. What do we mean by order? So order is just the highest derivative of xt that we're taking in the differential equation. So in this example here, we have our highest power, or highest derivative order, is 1. So this is a first order differential equation. Yt can pretty much be whatever the heck we want, as long as it's nothing too nuts. And for all intents and purposes, it can be whatever you want, pretty much. The caveat here is that when we find our particular solution down the road, the crazier this gets, the harder it's going to be to write that particular solution, because we're effectively just playing a guessing game to a certain extent when we look for that particular solution. So an example of nonlinear, because we said, hey, we're going to be dealing with linear ordinary differential equations. What the heck does it mean to be nonlinear? Well, here's an example of a nonlinear operator. It's the quadratic of x. So this obviously is involving the derivative of x. It's a differential, but it's nonlinear because it's utilizing a xt squared. So back here, recall, it's just something applied to x plus something applied to x plus something applied to x, okay? Here it's something applied to x. This is not quite just tacked on to it, right? It's not linear. It's not a linear operation. That box does not preserve x in that fashion. There are rules and proofs that you can do that are more rigorous for the definitions of linear, but that's not the focus of this course as much as I would like it to be. But we won't get into that too much. Okay, so a forcing function, as we mentioned briefly, y of t is our forcing function. It usually sits off to the side on the equation, and we deal with it after we've done some stuff. It forces our solution for x. And I mean this in the truest sense because what ends up happening is that as we change y, right, we move it around, change it around a little bit, it actually changes what happens with our, what we call the homogeneous solution of x. And we'll see that in one of the problems that we solve today. So it really does push x around quite a bit. Okay, so we generally are solving for xt. What we put in for this x may change, right? It's a variable. So frequently we'll see, it or vt. You can also say v of t or I of t, because we're dealing with current and voltages. We may see other functions in there. So just be aware that this is going to change. Our output's probably going to change because we're not dealing with x's and y's. We're dealing with other phenomena that are well defined. So just keep your head on a swivel there. And that should do it. All right. Just know that the thing that we're taking the derivatives of is the thing we're trying to solve for. There you go. Alrighty. So sorry, this is kind of a boring lecture today, guys. I don't have a lot of fun stuff in here. The most fun I have today is reverse Polish notation. So, take that for what you will. And I don't have any faces in front of me, so I can't see how bored you are right now. Alrighty, so the general assembly of our solution is first we've got to talk about the homogeneous solution. And the homogeneous solution is a function x sub h of t. And this is a solution to the differential equation when we set yt equal to 0. This kind of tactic should be no stranger to you with the superposition principle. So effectively, superposition, you kind of set it to a thing and you can filter through, if you want to think about it that way. We're kind of doing the same thing here. We're just picking a convenient yt, and then we'll tack it on after we're done and kind of fix everything together. So without getting into too much of the theory, that should be sufficient for us. Okay, so basically we have our operand and our operator. We're setting that equal to 0. For the particular solution, it's going to take a generalized form of yt. So, for example, e.g., if y of t is equal to, 3e to the minus 2t, then what xp is equal to be e to the minus 2t. That's usually going to be our first go at it. And there's some other rules that'll follow from there, but generally speaking, we're going to generalize what we have for our forcing function. Okay, complete solution, total solution, final solution, whatever you want to call it. It's basically Voltron, okay? You're just putting all of our pieces together. We have all these different homogeneous solutions. We have all these different particular solutions potentially. We're adding them all together because everything's nice and linear, so that makes our lives really easy. And, some assembly required. We're just adding all of those homogeneous and particular solutions to get our final solution. All right, initial conditions. The number of initial conditions we need to completely solve our equation is equal to the degree of the highest derivative, i.e. our order. So one such initial condition might be something like x0 of 0 is equal to 2. You may also see something like, the first derivative of x evaluated at 0 is equal to minus 3 or something. Characteristic equation. This is used to solve the homogeneous equation. So this gives us x sub h of t. The characteristic equation of an ODE is generated by replacing our derivative of xt. So we're just taking this part of the operator and our operand. Any constants that were out here, leave them alone. Because as it turns out, because it's linear, those are the only things we really care about. So we replace these guys with lambda to the n, and this is a true exponent and not a derivative, okay, like we have here. So it turns our ODE into a polynomial. You all should know what a polynomial is by now. But we solve for lambda just like you did in algebra in like 7th or 8th grade. Each root is going to get its own term. So if I have 3 lambdas, I will have 3 terms, and it will be a1, a2, and a3. Here's an example here. If lambda 1 is equal to 2 and lambda 2 is equal to, say, 3, then my homogeneous solution, all put together, is that first lambda. So it's a1. This is not defined yet. It's set by those initial conditions. We'll get to that in a minute. a1 times e to the 2t. And then the second part, a2, different one altogether. Gonna have to get another equation, another initial condition to isolate that other variable, to the 3t, okay? So just follow that form. Now there are some exceptions to this, and there's always exceptions to stuff. If we have repeated roots, we need to tack on t to the k. I'm not going to write the equation because the equation is actually more confusing than just the explanation. But basically, for each extra one that you get, you got to tack on an extra t. Okay, so if I have a root that appears 3 times, the first one is just a1. The second one is a2 times a t. The third one is a3 times a t times an extra t. And then note, we're going to need a lot of initial conditions for something like this, right? We need to fix all of these guys. There's just a ton in here. We have x to the n. If I use parentheses, or if you see parentheses like this, it's almost always referring to the nth derivative of x. This is the one you'll probably see the most often. You'll see this a lot, usually when you're talking about vectors or tensors or things like that. I don't see it too much outside of, I guess I've seen it a lot in like kind of mechanical applications and like fluid flow, some fluid flow dynamic stuff. But by and large, the pure sciences tend to favor this one. It really depends on background. All 3 of these you'll be responsible for knowing, but they're not that confusing. It's just 2 dashes, 2 dots, the number 2 in parentheses. They're all the same. But you'll always see this one when you have n greater than 3. Okay? Okay, one little edit in here I wanted to add is dx dt. So d squared x d t squared. So this is actually the other one that I forgot to add in. But look this up. So these two are kind of the Lagrange. version. So Lagrange basically created a lot of great uses for calculus, and in particular, we have a lot of operators and things that we have based on Lagrange's work that get used a lot in all kinds of physics, especially, and then applied to other areas. This is actually Leibniz notation, and I always mix up my I's and E's, of course. Leibniz. And this here is Newton's. So that, even though you didn't see this in calculus too much, you may see this in other more classical applications like mechanical engineering, and that's a holdover from the classical mechanics that he did. Like I said, I prefer Leibniz generally philosophically, and here's why. You can see that dx, dt, these actually represent like infinitesimal changes in x over infinitesimal changes in t. So the limit idea, or the infinitesimal idea, is inherent in the notation for Leibniz. So anyway, that's your math minute. Let's carry on. So let's finally write down a general methodology. So we're going to get to this part next time. So don't worry about that. But we're going to use the ODE first to create the characteristic equation. So for this, we're going to set yt equal to 0. That's what we do to create a characteristic equation. And then we do the replacement. Okay? dn dt n x t goes to lambda n. Makes things much easier. Some places you'll see r's, or I've even seen s's somewhere, I think. Lambda is generally the one that I see the most, and there's a couple different reasons for this. Part of it has to do with the fact that these are the natural, what we'll call the natural frequencies. We'll get to that in a minute. But lambda tends to be associated with waveforms or anything that involves a kind of a spectrum. So lambda is kind of a fun Greek letter. Anytime you see a lambda, you know you're going to be dealing with something wavy or wibbly wobbly. But but yeah, I think this is probably the most appropriate letter for this. To be honest, as a mathematician, I like this. So I will be using that for all my characteristics, even if that's not what you use in your ODE class. Okay, so next we're going to use the roots of the characteristic equation to find the form of the homogeneous solution. Boy, that's a mouthful. So basically, we find all those lambdas, we stick them into that that form that we had. This guy here. And that's it. We add them all together. Once they're added all together, you have to, dissect that polynomial. You should be able to... I expect you guys to be able to break apart a polynomial, a third-degree polynomial, relatively easy if I give you friendly numbers. There are some handy equations that you should be familiar with. Okay, my two favorite ones, by the way, for cubics are a to the third plus b to the third equals a plus b times a squared minus ab plus b squared, and a to the third minus b to the third equals a minus b a squared plus ab plus b squared. And if you're like, hey, you could factor these further, well, yes, you can, but you're going to get imaginary numbers, which is fine, because we love imaginary numbers, but for all real intents and purposes, this works. So keep those two equations handy. Don't forget that there's going to be some placeholder coefficients that we're going to have to solve for later on down the road. So don't be surprised like, hey, I don't have my full homogeneous solution. Of course you don't, because you don't have everything put together yet. Next, you're going to apply that forcing function And the way we do that is we try to find a form xpt that looks like yt. And then once you've isolated your homogeneous and particular solution, you put them together and form the total solution. So for that particular solution, by the way, all you're doing is popping in that generalized form into the differential equation and then solving for that generalization. So for example, for xp of t, all we do is pop it in to the differential equation and solve for the generalized form. So, like I said, for example, e.g., we're going to say xp of t is equal to be to the minus 2e. All you're going to do is pop that into the equation and solve for b. And then you just write out, say you find that b is equal to, 4. Then you're going to end up with 4e to the minus 2t is equal to your particular solution. That's it. It's really pretty straightforward to get the particular solution once you know what you're looking for, once you have that right form figured out. But sometimes it's really tricky getting that right form. I think most of the stuff we deal with is pretty easy, though. Okay, so again, we just add everything together. We get that total solution. Then we use our initial conditions at the very end. At the end. Not right after we get the homogeneous solution, at the end. Because as this particular solution changes, if we apply our initial conditions earlier, right, and our particular solution changes things, then the initial conditions won't have the correct effect on the homogeneous solution. So you need to make sure that you have everything put together before you apply any initial conditions. So have that nice generalized form. You can solve for these guys. But for the homogeneous part, leave those little placeholder variables alone until you get to this step. All right, that's probably the biggest mistake I expect to see. Hopefully by berating the point, I won't see it as much. So, sorry if it gets the audio gets a little weird. I got thunderstorm rolling in here tonight. But anyways, yep. So, let's see here. So, when we're doing our initial conditions, sometimes when we're trying to solve for those, we might have to do some fancy footwork. Shouldn't be too bad, but you may have to take some derivatives or move some stuff around in order to be able to apply those differential equations correctly or easily. And generally speaking, it's going to be easiest to, we'll get there. We'll show you some examples. All right. Congratulations. Now that you finally have your final solution, now you can pop it in and actually solve it and make sure that it works. Okay. This is one of the rare opportunities you do have a chance to verify that you have the right answer. Okay. So if you have time, plug it in and check it. I know on a test, you're probably not going to have time. I understand that, and that's okay. But in a real situation, if you got time, especially say the final exam, which is going to be take home, plug it in, make sure it works. Easy way to verify. All right, finally going to do some freaking examples here. All right, let's see what we use for an initial condition. Okay, so this is our ordinary linear differential equation, okay? And we're going to go ahead and I'm going to give you guys this initial condition of at 0, x is equal to 2, all right? Now, for most of these problems that we're going to be dealing with, and in particular for pretty much most of the course, our system really doesn't start before time t equals 0. for the most part. There's a lot of exceptions to that. But by and large, what you're going to see is that we don't like to deal with stuff before t equals 0. And there's a couple of reasons for that I'll get into later. First thing we do is we're going to derive our ODE. We did that. Check. Okay, use the ODE to create a characteristic equation. All right, let's do that then. So we're going to make a characteristic equation. We set this guy equal to 0, right? In this particular example, I'm going to go ahead and give you guys an easy one and say that y of t is equal to 0 for this. So as it turns out, this is the case anyway. We'll see what this does. Makes it really easy. So what is this? This is actually 2 times the 0th derivative of x, right? We're not taking any derivatives of x. So this is 2 times lambda to the 0, which is just 1. So life's good. That's easy. This is 3 times lambda to the first, because this is the first derivative of x. That's equal to 0. So now we have 0 is equal to 2 plus 3 lambda. Lambda, therefore, is equal to minus 2 over 3. That was easy. Our homogeneous solution then, x sub h of t is equal to a, some generalized variable. If we have more than one lambda, by the way, we just index these. But for single one, we just call it a times e to the minus 2/3 t. That's it. That's our homogeneous solution. Now, what we can do is we say, okay, let's pop this in, and we have xt is equal to xh t plus x particular t. Well, for our particular solution, we need a form of xt which is equivalent to or can render out something that looks like y of t, which is equal to 0. I have an idea. Let's let xpt equal 0. Problem solved. That's pretty easy. So actually, when you're given this condition, as it turns out, if y of t is equal to 0, xpt is equal to 0 too. So it makes life very easy. So our final solution then is just that, which is ae the minus 2/3 t. Okay, now we go ahead, we have our total solution, and we can solve for that initial condition. We've actually done the work for the particular. We've shown that's true. So let's do initial conditions. Okay, and I'm kind of color coding this a little bit. All right, here's our particular solution, and in green we had our homogeneous solution. All right. All right, so we apply initial conditions. X of 0 is equal to 2. ae minus, remember this is x of t, not our differential equation, just x of t. Evaluated at 0, well, e to the 0 is just 1, so this is equal to a, but we said, hey, this was equal to 2, so, oh, hey, a is equal to 2. So x of t is equal to 2, e to the minus 2/3 t. That's it. That's our final solution. So xt is equal to 2e to the minus 2 over 3t. Big box around it. Now go check it. Let's go ahead and specify a non-zero forcing function. Okay? Okay, so we have our homogeneous solution. 0 equals 2 plus 3 lambda, blah, 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 blah. We end up with our homogeneous solution is equal to a e to the minus 2/3 t. Great, we already knew that. Let's switch some colors. We know that x of t is equal to xht plus xpt. Let's solve for pt. Excuse me, x sub p of t, our particular solution. Our particular solution should take the form some constant times e to the minus t, because that's what y of t is. Yeah, pretty straightforward. Just replace the constant that's, okay. Just replace the constant that's up there if this is your yt. And you can look up online some of these other forms and stuff. If I give you something that's kind of out of left field that we haven't been hitting very frequently, I'll probably throw you a bone on how to build that particular solution if it's required of us. All right. Okay, so let's plug this guy into our differential equation. We have 4e to the minus t, that's our y, right? This is our yt. This is equal to 2 times x, but it's x, our particular solution, not the total solution, just the particular solution, because the particular solution can stand on its own. All right, so we have p, what am I doing? b e to the minus t, that's our x, plus 3 times the derivative of b e to the minus t. So that's actually minus b e to the minus t. That's the derivative of this guy. Pop it in there. And now we solve for b. This actually isn't too bad. We end up with a bunch of e to the minus t's floating around. We can actually get rid of those really easily. Just divide them out. And we end up with 4 is equal to 2b minus 3b. Okay, if you can't solve this, I can't help you. So, good luck. 4 is equal to minus b. B is equal to minus 4. Okay? So this gives us x p t is equal to minus 4 e to the minus et, or e to the minus t. I haven't made an et joke yet. I'm sorry, Steven Spielberg. All right, so now we're going to move into our initial conditions. So let's write out our full form. We have our homogeneous, let me write this again real quick just to summarize, plus xpt. So xt is equal to our homogeneous, which is a e to the minus 2/3 t, plus our particular solution, which is actually minus e to the minus t. And now we apply the initial condition that this is the case. So we didn't really use this part yet. In this situation, you can see that it didn't really matter too much, but it is something to be careful of and something to be aware of. I'll just leave it at that. We'll probably see some down the road. Well, we will see some down the road where it does matter. So we'll address it, I promise. But didn't matter too much here. Okay. Here we go. We just solve for a now at this point. We have times 0 minus 4e to the minus 0 equals 2. And so a times 1 minus 4, e to the minus 0 is 1, equals 2. So a, arrows, not equal sign. By the way, don't write equal signs for equivalent expressions. Use a double, like an arrow or something. So a is equal to minus 2. Well, it was, what was it before? Oh, shoot, it was 2 last time. Oh, we must have made a mistake. No, we didn't. It was forced to change. I wonder what changed, or what forced it to change. It's the forcing function. The forcing function forced it to change. That's why we kind of call it the forcing function. There's other reasons too, but yeah. So our forcing function actually dictated, even with the same initial conditions, what happened to our homogeneous solution. That's pretty cool. Just by changing this guy, we were able to change our general solution. You can see where this is probably going. So let's write this out in red. Xt is equal to, I always try to write the homogeneous solution first. So minus 2 e to the minus 2/3 t plus, minus 4e to the minus t. That's it. And then I leave you checking it as an exercise because I hate doing that. I'm too lazy. I'm a mathematician, okay? I'm too lazy. I'm also an engineer, so I shouldn't be that lazy, but oh well. All right, continuing on our adventure, we have the following. We already know for this particular problem, because we've solved it over and over again, that our homogeneous solution is a times e to the minus 2/3 t. When we go to look at our particular solution now, we see that it should be some constant times e to the minus 2/3 t, based on what we know for our rules that we've established. The problem here, though, is that these two guys are of the same form, exactly the same form. They just have different constants. And if you recall, when we were doing the homogeneous solution, if we had repeated roots, we wanted to avoid that, and so we would tack on a t, or if we had 3, t squared, etc. So in the case of the particular solution, we actually need to do that as well. So the general rule of thumb is that if there's any duplication in the assumed form of our of our particular solution, with the solutions from the homogeneous, then we just multiply them by t, or if necessary by t squared or whatever, to remove that duplication. All right, so we're going to go ahead and do that. Now notice that last time we didn't need to do that, because what we had here was of a totally different form. It's e to the minus t, not e to the minus 2/3 t. So it must have that same frequency, if you want to think about it that way, up in the exponent of e. Alrighty, so this actually then becomes bt e to the minus 2/3 t. We can go ahead and solve for this, this b, because we know that with a particular solution, we can go ahead and plug it on through and solve away. We don't need to put everything together for the particular part. Okay, so we have 2 times b t e to the minus 2/3 t plus 3, and now we have to do the differentiation with respect to t, so we're going to have to use our rules from calculus, right? So we have the product rule. I'm going to go ahead and do the derivative of t first. And then I'm going to carry along that t for the ride. So it's going to be bt, and then we take our derivative with respect to e to the minus 2/3 t, so minus 2/3. And there we are. All right, fortunately in this particular example, we get some nice cancellation happening. So we end up with just 3b e to the minus 2/3 t. Now, I know you're saying, hey, what happened to our b, t, e to the, whatever. Don't worry about that. We're not doing that right now. We know what the form was. All we're looking for right now is b. So we just got to solve. All right, divide out by that e to the minus 2/3 t. Assuming that we can do that nicely, we can. So we're gonna. And divide by 3. All right, so that just becomes 1. And what do you know? B is equal to 1. Nice. We put it all together. We have that a still hanging around because we need to put everything together before we can solve for those. B is equal to 1, so we just have plus t e to the minus 2/3 t. And you can solve the rest from here. Yeah, actually the book doesn't the book doesn't even have it in here. Okay, so yeah, the book is as lazy as I am. Go figure. But you can solve this. We've done it before. So easy. We have that if we had an initial condition, which I didn't give you guys. All right, perfect. So I forgot to write that down anyway. So if you had an initial condition, say something like that, then you would pop it in. Okay? All right, losing my mind here. Let's keep going. All right, I'm going to skip ahead to the last example in the book, just to give you, one more piece before we go. And this is a higher order ODE. I'm going to write the form of this a little bit differently because I'm actually going to do an example later on here today that uses the notation that's in the book. So don't worry if it doesn't match up exactly. So we have this is equal to 2x of t plus 3x prime t plus x double prime t. Okay? And our initial conditions that are given to us are x0 is equal to 2 and x prime at 0 is equal to 1. So what do we do for this? This is kind of a bear. Well, we do what we always are supposed to. We're going to look at that homogeneous first. So we're going to solve for our characteristic equation first. We end up with 0. Remember that our other side, our yt, is set equal to 0. And we just plop those lambdas in here. Okay, and this should be a pretty easy one to just factor in your head. This is kind of stuff I expect you to be able to do. This is, 2 plus lambda times 1 plus lambda. You can see that lambda plus 2 lambda gives you 3 lambda. So you can build that pretty easily. So lambda is equal to minus 2. Lambda is equal to minus lambda. Lambda is equal to minus 2 or minus 1. All right. So now we have our particular solution. Our particular solution, looks like this. I should finish what I started here over here, right? So this is actually equal to a1 e to the minus t plus a2 e to the minus 2t. Okay, now you can see the contradiction pretty clearly. That's not going to work. This form matches this guy. So we need to modify that. So this becomes bt e to the minus 2t. And from here, what we do is we solve out. So we have 3 e to the minus 2t. And you can do some work. Let me at least write it out for you guys so you know what exactly you're supposed to be solving. So 2 times bt e to the minus 2t plus 3 times the derivative of bt e to the minus 2t plus the second derivative of bt e to the minus 2t. I'm not going to solve this out all the way here. Suffice it to say, it's in the book. You end up with the following. Oops. Got a little bit ahead. Sorry about that. We end up with the particular solution equal to minus 3 t e to the minus 2t. So you do some work, and you end up with d is equal to minus 3 here. It's not too bad. You should be able to... Mostly this, the e to the minus 2t is going to cancel out through there, so it's really just a very simple algebra equation at a certain level. Okay, now that we have that, we assemble our total solution, and we end up with minus 3e, oops, okay, t e to the minus 2t plus a1, e to the minus t plus a2, e to the minus 2t. All right, this is where it gets kind of tricky. So we need to evaluate this at 0. So we say x of 0, just kind of give myself some space here. X at 0 is equal to 2, which is equal to minus 3 times 0. I don't care about the rest, e to the whatever. So this is all 0, plus a1, e to the 0, plus a2, e to the 0. All right, so I end up with 2 is equal to a1 plus a2. Well, that's nice. That's not bad at all. Except it doesn't actually tell us anything yet, right? So what are we going to do? We have this x prime of 0 is equal to 1. Well, we just take a derivative. That's all we need to do. So we're going to go ahead and write out our derivative. So we're going to take this expression down here and take its derivative. So x prime of t, we know what its form is. These are just constants. They'll just go along for the ride, no big deal. X prime of t is equal to minus 3 e to the minus 2t. Got two parts for that first term, don't forget. And then minus 3 t e to the, oops, I gotta carry that through properly. There's our t, times minus 2 e to the minus 2t. And then plus, well, it actually ends up just being minus a1 e to the minus t, and then minus 2a2 e to the minus 2t. Ugh, there's a lot of stuff there. Well, as it turns out, it's not too bad, because we're evaluating it at 0, and that's equal to 1. So we're going to hold this for a second. So that's all just equal to 1, so we plop in 0, we end up with minus 3 e to the minus 2 times 0 is just 1. And then this is 0. This whole second term goes to 0. Our third term is just minus a1. Our fourth term is minus 2a2. So we end up with 4 is equal to minus a1 minus 2a2. You should be able to put those 2 and 2 together and figure out what's what. So let's go ahead and pop in a substitution for a1. So from up here, we know that a1 is equal to 2 minus a2. So we have 4 is equal to minus 2 minus a2 minus 2a2, right? Which means that 4 minus 2 plus 2, so 6 is equal to a2 minus 2a2. So a2 is equal to minus 6, which means that a1 would be equal to 8. And that's it. Our final bit here, I'm running out of space. I'm so sorry. So I'm going to take these. Oh, I hate doing this. I really can't shift stuff around, though, to find a good spot. So I don't want to change it to a new slide. Okay, so we pop this into our expression for the total solution. We have a1 is equal to 8, so that's multiplied to e to the minus t, and a2 is equal to minus 6, which we multiply to e to the minus 2t. Add that to our particular solution for the first term, and that gives us everything that we need to solve this problem. All right, everybody. Speaking of the homework, please go attempt it. There's a very interesting problem at the beginning of this problem set that kind of doesn't fit in here exactly, but will provide some much needed enlightenment for how to solve future problems and how to deal with a complex plane. It's a good review for complex numbers if you haven't dealt with them in a while or something. I was going to do this problem. I think I'm completely out of time at this point, so I've probably run way over. I've recorded longer than I've ever recorded before. So stay safe out there. Have fun this summer. And I guess we have our second quiz coming up here soon. So if you're doing these lectures in order, good luck on that. And yeah, thanks for watching.